In this video, we're going to look a little bit more about our two charged plates. We've used these in several examples. The idea is I have two conducting plates. I've put a positive Q on one plate and a negative Q on the other plate, where Q is the same magnitude, right? Obviously different in sign. And I'm going to further restrict what I can do with these plates. Let me see if I can draw it in 3 dimensions here. I'm at an angle, so it's always sketchy, but whether or not I can do this, no pun intended, although that was a good one. Alright, so I have these two parallel plates of a conducting material. They have some area A, right? That's the area of this side, which is, tilted at an angle to you. And they have some separation distance D. So what I've been assuming is that D is really small. I'm still going to assume that because I can't draw it really small because it wouldn't make any sense. But usually D is really, really, really small, the distance between these plates. Okay, and of course we know that there's an electric field that develops between these plates that looks like that. It's nice and uniform as long as we stay away from the edges. Now, what I'm going to ask now is, how in the world did the charge get on these plates, in the first place? Probably what I did was I connected this to a battery. Now, we have not talked about batteries yet. We will talk about them a lot when we start talking about circuits, but this is kind of where that whole thing starts. So let me introduce you to the symbol, the electrical symbol for a battery. It looks like this. It's just two lines, one of which is larger than the other. And on this diagram, I'm going to write that the large line represents what's called the positive terminal of the battery. This represents the negative terminal of a battery. If you look at a battery, and I just so happen to have a remote control here, so let me pull out a battery and show it to you. This is a AAA. Let's make sure you can see it. So if you look somewhere along the battery right there, there's a positive symbol. It's on the little protrusion there, positive symbol there, and then on the other side, sometimes they write a negative symbol, sometimes they don't. Looks like on this one they didn't. But a positive side over here means that the negative side is over here. Now we're not going to worry too much about the actual operations of a battery, but what you need to know is that for our purposes, they act something like a pump. We're using gravity a lot as an analogy, so I want you to think of charge moving around here like water flowing through pipes. And if water is going to flow, we need some sort of mechanism to make it flow. So you can think of a battery like a pump. I'm usually going to think of a battery as a hill, right? I always think of electricity as a hill because that works with my understanding of gravity, that things flow downhill. Well, in a circuit, things flow, quote unquote, downhill, right? Where the positive terminal here is going to be the top of the hill, the negative terminal will be the bottom of the hill, and what I'm going to find is that charges will flow out of the positive terminal around and back into the negative terminal. And then the battery acts as a pump to pump the charges back up to the top of the hill. We're going to investigate that analogy a whole lot in the days and weeks to come. But for now, just understand that what this battery is going to do is it's going to push out positive charges from its positive terminal. Now, when I hook this up, the battery has some sort of potential difference, right? Which is going to actualize the potential of these charges to flow, and they're going to start flowing. And when I hook this up to the battery, I should point out, there are no charges. The minute I hook it up, it's got nothing on it. But as soon as I connect this battery, I get a positive charge, a stream of positive charges that flow out of this positive terminal and start to deposit themselves on this plate. They can't go any farther, right? Because there's a gap there. But as soon as I put one little bitty positive charge here, it starts to exert an influence on this plate. There's an electric field. So there's some positive charge over here that's like, nope, I'm out of here, because it feels the repulsion from this positive charge that I've put on there, and it leaves and flows around, right? So then I put another positive charge on this plate, and a positive charge leaves. So I'm leaving this one with a positive charge, this one with a negative charge. Notice every positive charge I put on here kicks off one positive charge. So I charge them up equally. One positive charge deposited, one positive charge kicked off, so on and so forth. Now, if I'm the positive charges being forced onto this plate, I'm not really happy about that. Positive charges don't like to be near each other, right? So each charge I put on this plate takes more and more work to put there. The first one, no big deal. Deposit it, we're good. The second one, I've got to work a little bit. The third one, I've got to work more. The fourth one, I've got to work more and more and more and more and more. So there is a hard limit to how much charge I can put on this plate. So conversely, that means there's a hard limit to how much charge I put on this plate because they're the same charge. And so at some point, I'm going to put the last possible charge I can force onto this plate. And then the current, the electricity, the charges stop flowing. So I connect this thing to the battery, charges flow, it starts to charge up. The charges are slowing down because it's harder. Finally, I reach the last charge I can put on here, and the charges stop flowing. At that point, this thing is fully charged. Now, let's think of what some things could be that could change how much charge I put on here. The first thing I can think of is, well, let me write this down. What can change the size of Q, where Q is what we'll call the charge on this system, right? What can change the size of Q? Well, the first thing I can think of is I can maybe put a bigger or a smaller battery on this thing, right? A bigger battery is going to be able to force more charges on it. A smaller battery will force fewer charges. So if I'm just looking what can change the how much charge I put on this thing, the battery is a good place to start. How much voltage do I have to push around the charges? Fair enough. Another thing I can think of is the distance between the plates, right? Why would that make a difference? Well, remember the reason the positive charges are leaving this plate is because they feel an influence from these charges. That influence is an electric field. And of course, the electric field depends on distance, right? It's distance dependent. So if I make this thing closer, if I bring it closer, the electric field gets stronger and more charges get kicked off. If I make it farther apart, they don't feel the influence as much. The electric field has gotten weaker over here, and I can put fewer charges on there. So D works just fine. Another thing, the area of the plates, right? It just stands to reason. If these charges don't like to be near each other, if I give them more space, if I make the area of the plate bigger, more of them can get on the plate, right? If I make the area smaller, fewer of them can get on the plate. Fair enough. All right, so we see here that Q, the amount of charge I can put on these plates, is proportional to several things. It could be directly proportional, it could be indirectly proportional, but it's going to be proportional to these three things. So let's investigate that a little farther. The first thing I'm going to do is name this system. This is called a capacitor. Specifically, this is a parallel plate capacitor. There are others, but this is a parallel plate capacitor for obvious reasons. It has parallel plates, right? So no big mystery there. What does capacitor mean? Well, you might recognize the root word capacity. What this is a charge storage device. Now, we don't really care about charges, but what we do care is energy. And where there are charges, hopefully we've seen there's electric potential, which means there's electric potential energy. So what we really care about is storing energy. You can think of it as storing charges as well. But this thing has some sort of capacity to store charge, which is where we get the term capacitor. So what I'm going to say now, let me give you the definition of capacitance, and I'll write out that word. The capacitance of a capacitor is the way we characterize its capacity to store charge. The symbol for capacitance is C, and what I can say is that the capacitance is going to be defined as amount of charge per unit voltage. That's not a volume, be careful. A lot of times when we see this V in the denominator, we're dealing with a density, and that's a volume. This is voltage. Charge per unit voltage gives you the capacitor, right? Or sorry, gives you the capacitance of this system. Of course, we can rearrange this how we want to. Q is equal to CV. V is equal to Q over C, however you want to rearrange it. This is the definition of capacitance. So what have I done? I've taken care of the relationship between this guy and charge. However, I still have some other things to look at. And as it turns out, I'm not going to prove it to you, but for a parallel plate capacitor, right? And a parallel plate capacitor is the only one we've looked at. It's the only one we're probably going to look at. And it's the only one for which the terms A and D make any sense, right? Because this is an area of a plate, distance between two plates. For a parallel plate capacitor, it turns out that the capacitance is equal to this, epsilon naught, our good old electric permittivity, A over D. So this is a general definition of capacitance. This is a specific capacitance for a parallel plate capacitor. We like this one because this is solely based on physical parameters. As it turns out, even though this equation is valid for the system also, I can determine the capacitance just by physical parameters. That's actually really good news if I'm building a capacitor, because then I know exactly how much material I need, and I know exactly the distance to place the material apart from each other, apart from the other one. So these two equations are very important for the capacitance of a capacitor. The symbol for a capacitor, I showed you the symbol for a battery. The symbol for a capacitor looks really similar. It's two lines that are the same length. Remember, the battery has different lengths. The capacitor has the same length. And that might give you some sort of clue as to what capacitors do, right? What does a battery do? Well, it provides a current. It's a source of charges, if you want to think about it. It makes charges flow would be a better way to do that. So let's think about this. Let's see what happens to this. After I charge up the capacitor, right, and I have, it's completely charged, what if I put in something like this? Now, these are more electrical symbols, but you can probably see this pretty well as a switch, right? What is going to happen if I close this switch? And let's furthermore assume that as I close this switch, I've got some sort of mechanical device that will actually disconnect this line. And so I'm taking the battery out of the equation. So I use the battery to charge this thing up, and then I flip a switch, and now my system looks like this without a battery, but a closed, we call it a closed circuit, but I've got a connected wire here. What's going to happen? Well, you've got a lot of positive charges here that don't really want to be near each other. So what are they going to do? They're going to start flowing. They're going to flow from here around back to where they want to be, this plate. And they're going to flow until all of the excess charge has gotten off of this plate, and I have a neutral plate again, just like I would have a neutral plate over here. So basically, current is going to flow. The charges are going to flow. Well, isn't that what I did here with the battery? I made charges flow. And now I'm saying if I close this switch, charges are going to flow the other way. And that's exactly why we like capacitors. In point of fact, the charges are going to flow, and they're going to flow really, really, really quickly. So that actually is what we use capacitors for usually in real life. Batteries charge things up, but they usually do it rather slowly. Capacitors represent a really, really quick discharge of current, right? If I flip the switch, this charge is going to jump off. The battery kind of controls it and makes it go slowly. But if I close this switch, it goes really, really, really quickly. So what does that mean? If I need a large amount of flowing charges, in the electrical term for that is current. We'll get to that in a few chapters. If I need a large current that's delivered really quickly, usually the best way to do that is with a capacitor. These have all sorts of uses. In the old days, when dinosaurs roamed the earth and we didn't have iPhones, right? Cameras with film were a thing, and more importantly, cameras with flashes were a thing. Now on your smartphones, the flash is an LED, which may or may not use a capacitor. I'm actually not really sure. But in the old days, they had actual light bulbs. And you needed to produce a lot of light in a very small amount of time. So what they would do is they would have a capacitor in the camera, which when you clicked the shutter, click, would discharge a large amount of current to the light. It would discharge the capacitor, deliver a large amount of current to the light bulb. It would light up really brightly, but just for a second, because that charge is moving so fast. And then you would take the picture, and then the light bulb would go out. But if you've ever used one of those cameras, after you take the picture, you usually hear a really high whine. I'm not going to try to do it, but you click and then whine, 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 whine. I'm saying whine, like a really high-pitched sound. That sound is actually the capacitor recharging. You're putting more current from the battery. You're using current from the battery to recharge the capacitor and in preparation for your next picture that you have to take. So these are used all over the place anytime you need to deliver a large amount of current in a short amount of time. All right, so let's furthermore look at a couple more things here. Now, I know that since there's an electric field across these plates, this is after this thing is charged, I know that since there's an electric field, I measure a voltage across these plates, right? So, after it's charged, anybody care to take a guess what voltage I measure across these plates? I measure the voltage of the battery. Think about it. If you have a 9-volt battery here, and you're charging up the plates with a 9-volt battery, there's only so much charge that 9 volts can put on it. It stands to reason then that as the charge builds up, and I'm starting to develop a potential across these plates, after the charge stops flowing, I've developed the same potential as the battery. So I've developed the same potential, although to be really technical, if this is a 9-volt battery, what I measure across here is negative 9 volts, right? It opposes, I'll write this down, the potential, just one C, across the plates, opposes the potential from the battery. That should just stand to reason, right? If I charge this up with a 9-volt battery, I develop a negative 9-volt potential across these plates. If I charge these up with a 2-volt battery, I develop a negative 2-volt potential across the plates. That is after it is charged, right? While it's charging, this is going to rise. It starts out at 0 volts, and then negative 1 volt, and then negative 2 volts. So this is a 2-volt battery. It's going to get to negative 2 volts, but negative 2 volts will be its final value. So usually you would see that asked, after this capacitor has been connected for a long time, what is the voltage across the plates? And if you have a whatever volt battery here, it's just the negative of your battery voltage. And the language there is long time because it's had time to charge. Sometimes they might even say a charged capacitor, right? So if this is charged up to, say, 9 volts, you have a 9-volt battery, charged up to 9 volts, when you flip this switch, this acts as a really quick delivery 9-volt battery. All right.